Welcome back to another video, and we are in an improper integral state of mind once again, 2 nights in a row. We're going to go a little deeper, dive into some other cases here tonight. Just to review, yesterday we looked at the first case yesterday where we said one of the bounds, or maybe even both of the bounds, were going to be equal to infinity or perhaps negative infinity, but something of that sort. Today we're going to take a look at cases where there's an infinite discontinuity at or within the limits of integration. Okay, now just to clarify, infinite discontinuity sounds a little overwhelming. All that is an infinite, and I'm going to abbreviate here a little bit, infinite discontinuity is just a fancy name for a vertical asymptote. Okay, that's all it is. That's all we're really trying to say, is that there's either a vertical asymptote at one of the bounds or within one of the bounds, thus creating. Now, whether you're talking about case 1 or case 2, basically what we're creating in all of these situations is an unbounded region. Okay, an unbounded region where perhaps our common sense is telling us that the total combined area should be infinity. Okay, but we've seen some cases where it does converge to a finite number. Just like the other night, though, our ultimate goal on each of these problems is to decide whether the given integral converges to a finite amount of area or whether it diverges to a infinite amount of area. Okay, diverges means we got infinity for an answer. Converges means we actually got a finite number for an answer. Okay, we're going to look at 3 generic cases, what we're kind of getting ourselves into today. Case number 1 says we might have an infinite discontinuity, okay, at the upper endpoint, which is commonly referred to as b. Okay, if you think of your generic integral going from a to b, we're saying that there's a vertical asymptote when you hit b. So in other words, we'll try ourselves a little picture here. Perhaps we have this big vertical asymptote right there at b. The graph comes in and approaches, goes upward, and we say, you know what, we want to integrate from a to b. And therefore we have this unbounded region here with a leak right at the top of that region that just goes on forever and ever. When you get an integral like this, okay, we're going to rewrite it. We're going to say, instead of saying the integral from a to b, okay, what we're going to do is we're going to rewrite that. I'm going to scooch down here a little bit. We're going to say that's really the integral from a to c. You're wondering where in the world c came from. We're going to define that limit as c approaches b from the left side. Notice we said left side because when we talk about this region right here that we shaded in, that shaded region lies just to the left of b. That's why we defined c as approaching b from the left side. That little left negative sign is very, very important to us. Okay, our second example is very, very similar to that. Switch back to the black. Our second one says, well, what if you have an infinite discontinuity, okay, at maybe the lower bound, a. Okay, so just to draw ourselves a visual image, maybe we'll say here's a, that's where the vertical asymptote is lying. The graph looks something like this. We cut it off at b, and we said, you know what, I want to find all of this area right here. Unbounded region because of what's happening up here at the top, and we're just going to say that the integral from a to b needs to be rewritten as, okay, and hopefully you maybe have guessed this one, we're going to say from c to b, and we're going to define c as such. We're going to say the limit as c approaches a. Now try to figure out from which side do we want to approach a from. This shaded region lies just to the right side of a, so we're going to approach a from the right side. Okay, now before we go on to the third one, I just caught one of my mistakes. Let's go back up here to the top, and I wrote IF for some reason. Let's go ahead. This is supposed to say infinite discontinuity, which is another fancy name for a vertical asymptote, of course, but that should have been a D right there as I was trying to abbreviate discontinuity. Okay, let's go down. We're going to try to represent our third one. And ladies and gentlemen, I want you to put some mega stars next to this case right here. This is what they've put on the AP exam the last couple of years. It's very sneaky, it's very devious, and I will say this, like when they put a partial fraction on the AP exam or they put an integration by parts and we use tic-tac-toe, they tend to be very, very straightforward, okay? Of all the ones we've done in class, they tend to go very easy on us. However, these improper integrals, I've seen just the opposite occur. They tend to be very, very hard on us, and instead of giving us easy ones, they like to try to be very sneaky. And here's what's going to happen. They're going to give us one where the infinite discontinuity is somewhere in between the bounds A and B, okay? In between A and B somewhere. So if we're trying to represent this visually, there might be a vertical asymptote right here at, we'll say C, for lack of a better name. And then the graph swoops up like this, it swoops up like this maybe, and the integral is wanting us to go from A all the way over here to B, and there's somewhere in the middle of that region is this vertical asymptote. And so we're okay, we need this region right here, plus this region right here. Both of them are unbounded. Both of them have leaks at the top of their graphs here. Basically what's going to happen, we're going to rewrite this one integral that says integrate from A to B. We're going to rewrite that as the sum of two other integrals. We're going to say this is the integral from A to C, okay, plus the integral from C to B of that function. And then, of course, we would then have to go redefine both of those in terms of a limit. We'd have to, the first one we'd say maybe we'd approach C from the left side, and then on the second one we'd approach C from the right side, and we'd rewrite them in terms of a limit. And the key to that one is that both of those integrals have to converge in order for the entire sum of the two to converge. So basically what's happening here, if you work that first one out and it ends up diverging, say, then you're completely done. You don't even have to go worry about the second one, because once one of them diverges, then the entire thing diverges. Again, our main objective on all of these improper integrals is to decide whether or not they converge to a finite number or they diverge to infinity. Okay, finally time to roll up our sleeves and get after one of these problems. We've got the integral from 0 to 1, and then dx over the cubed root of x. And I'll tell you, I think these are more challenging to identify than the ones last night. Last night, when you immediately, if you saw the infinity sign up here, you said, oh, definitely unbounded region, definitely an improper integral, yada, yada, yada. Tonight, they're not so friendly, and they're not as obvious. You see bounds of 0 and 1, usually your first thought is not an improper integral. But consider that denominator, okay, and consider this graph. This particular function has a vertical asymptote at x equals 0 because you're simply setting the denominator equal to 0. Okay, let's just remind ourselves that vertical asymptote means we set the denominator equal to 0 and then we simply solve for x. And this particular function behaves like this. And so we're starting at 0, we're ending at 1, and we're talking about this region right here. So we're going to rewrite this. We're going to say let's integrate from A to 1 or from C to 1. It doesn't really matter what constant you use, okay? As long as you define that constant as such, the limit as A approaches 0 from the right side, because this region here lies just to the right of 0. Now from there we're just going to be very meticulous about our notation, okay? Very careful, very detail oriented here. Now I'm integrating x raised to the negative 1/3. Which means if I add 1 to that exponent, I'm going to get 2/3. If I multiply by his reciprocal, I get a coefficient of 3/2. Just using some very straightforward power rule there. Lower bound of A, upper bound of 1. Limit as A approaches 0 from the right side. Okay, we plug in a 1, we work it out, we get 3/2 minus, and now we're going to plug in the lower bound as the first fundamental theorem suggests I do. And now it's a matter of trying to evaluate this limit problem. Who'd have thought we'd be this deep into calculus and we'd still be relying on what we learned about limits last year. But the bottom line is here, when we go, I'm not actually substituting a 0 in for A, although it kind of works for this problem. We're really focusing on the fact that A is approaching 0. So I'm thinking, in the back of my mind, I'm kind of thinking that A is equal to like 0.0000001. Something of that nature is what I'm essentially thinking. And as I substitute into this quantity right here, it becomes so small that it is essentially a 0. Okay? So 3/2 minus 0 gives me 3/2. That's a finite number, therefore this improper integral happens to converge, okay? So again, we're claiming that an unbounded region has a finite amount of area, again, blowing my mind away. Okay, here's our second example. It says we're going to integrate from -2 to 0, the function 1 over x cubed times dx. If we're trying to visualize this graph, 1 over x cubed, it's in the first quadrant, it's in the third quadrant. It's very similar to 1 over x. The only thing that's different is the rate at which it approaches those axes and those asymptotes. The region we're concerned about starts right here at -2, and it's tucked away down there, kind of in the corner of the third quadrant. And again, because of what's happening right here and the behavior that graph exhibits, we have an unbounded region. So I'm going to rewrite my integral starting at -2, ending at b. Again, I could have used the letter c, it doesn't matter. In fact, I technically could have used the letter a, as long as you're using some random constant. We're going to define that as such. The limit as b approaches 0 from the left side of 0. And then we're trying to integrate 1 over x cubed, also known as x to the -3. Being very meticulous about my notation here, we're just going to continue to bring down that limit. Okay, the antiderivative says we're going to add 1 to that exponent. We're going to divide by that new exponent. Bounds of -2 and b. Limit as b approaches 0 from the left side. We'll plug in our b. Now, as I plug in that b, I'm going to write it as -1 over 2 times b squared, just so my exponent's positive, minus a -1 all over 8, I believe. You'll have to check my number crunching there, and if I did that wrong in my head, you can pick on me tomorrow. The bottom line is we're definitely getting a finite number on that second term. What we want to be very careful of again here is we're not really substituting a 0 in for b, and in this particular problem it really matters. On the last problem we could have just kept it simple and said, you know what, plug a 0 in for a and go with it. But here it's going to pay off. We're technically, remember, we're saying b approaches 0, so b is technically something of the sorts, 0.0. Now it's coming from the left side, so I should say -0.0000001. The bottom line is, okay, by the time I square the b, it's positive, but it's so microscopically small, and it's got so many, it's 0.000 with, an infinite amount of zeros before that 1 comes into play. -1 divided by that number actually turns out to be infinity, okay? We're talking about 1 divided by the smallest number ever created in the history of math, okay? Plus 1/8. I don't care what you're adding to that, it's still infinity. In fact, it still should be negative infinity, I should say. -1 divided by a positive number because we squared it. And again, we're getting negative infinity, therefore this improper integral diverges. Okay, our third example is by far the most devious, and I can't stress this enough. This is going to be on the AP exam, folks, okay? And it is a well-disguised improper integral right here. Okay, if we're in a hurry and we're not on our toes, we're not going to recognize this one because the bounds are so well behaved. It's easy to just start integrating and plugging in the bounds, and I promise you are not going to get the right answer if we don't identify it as an improper integral. And we'll probably learn this the hard way once or twice, and after we get sick of making that mistake, we'll be a little more disciplined and we'll identify. But the bottom line is, if you set that denominator equal to 0, which is something we should always be doing anyway in our heads implicitly already, you're going to decide that there's a vertical asymptote right at x equals 0. So what we've got, this particular graph looks like this and this. Okay, we're integrating from, say, -1 right there all the way to +2 right there. We've got an unbounded region there and another unbounded region over here. So we're going to rewrite this as the sum of two unbounded integrals. I'm going to say the integral from -1 to 0. Okay, whoops, that should be an x squared. Plus the integral from 0 to 2. And remember how we said both of these have to converge in order for the original one to converge? What I'm going to do is, here's a good example. Let's just tackle that first one. Let's solve that all the way through instead of working on both of them simultaneously all the way through, okay? So we're going to put all of our energy into figuring out this first one. First thing I'm going to do is I'm going to rewrite it as the integral from -1 to b, limit as b approaches 0 from the left side. Okay, and that's dx over x squared, which is actually x to the -2. Using my power rule, we could say that the antiderivative is, let's see, -1 over x, or -x to the -1 power. Okay, always seems to be more helpful to write it in terms of a fraction. Okay, one more time here. Limit as b approaches 0 from the left side. We've got negative 1 over b minus negative 1 over negative 1. How convenient. Anyway, negative 1 divided by b. Now again, b is, approaching 0, so it's like negative 0.000001. 1 divided by that microscopically small number actually turns into infinity. Okay, it's actually a positive infinity this time because a negative divided by a negative. We end up getting infinity. Therefore, just that first integral diverges. Therefore, okay, take a look. Let's go back up here, okay? Let's say we just concluded that this bear diverges, okay? It's an infinite amount of unbounded area. So then it does not matter what this guy does. It does not matter. Don't waste your time solving this one, okay? The entire integral automatically diverges, end of story. Okay, the last thing I want to finish tonight with is a special family of improper integrals, and later on when we tackle the Mount Everest of Calculus 2, known as our chapter on sequences and series, this P series is going to be a very big component of it, and it's strongly related to what we're talking about here with improper integrals, and so I just want to tackle it before we move on. And that family is the family of functions known as 1 over x to some power, okay? It could be, and I've listed 3 examples here, one in red, one in orange, one in green, and I want to talk about the relationship of these crazy functions and it just exactly why they're going to be so important for us in the long run, okay? First of all, what do all these graphs have in common, and we're interested about what's happening in the first quadrant only, really. What do they all have in common? Because they behave so similarly, yet they have some sharp contrast to them. I'm going to start with the orange one here, 1 over x. Okay, this graph is what we like to say asymptotic to both axes. Okay, also has a mirror image in the third quadrant, but we could actually care less about that tonight. Okay, and it happens to pass right through that point right here, 1, 1. I think you'd agree. Now, how does the red graph compare to that? How does the red graph compare? Well, actually what happens, that red graph starts off closer to the y-axis, cuts through that point, and then stays higher above the x-axis. Okay? And we can just call that 1 over radical x. Now the third one, the green one, is actually just the opposite. He starts farther away from the y-axis and then cuts through that point and then gets closer to the x-axis as we approach infinity, okay? So what you're learning is that as similar as these graphs are, they all approach the x-axis at differing rates, okay? And we're really interested in what's happening between 1 and infinity, okay? That's the part of the graph so we're going to focus on over the next couple of months. And basically we're going to find out that the orange graph diverges, okay? Anything above him diverges, but think of that orange graph as kind of like the Great Wall of China, I guess, for lack of a better words. That's the dividing line. Any graph that gets underneath that orange one approaches the x-axis fast enough to converge. Okay, let me say that again. Anything that gets underneath that orange graph converges because it's approaching the x-axis just fast enough so that gap in here gets so small that it gets irrelevant. But essentially the gap between the orange graph and the x-axis is big enough to be relevant and therefore diverge. So it's kind of a wild thing to try to wrap our brain around. We're going to go ahead and try to prove that here in a few minutes and show you, for which values of p does it converge and which values of p does it diverge. So we're going to talk about this family of functions right here, and we're going to integrate it, and we're going to keep it very generic in terms of p. All right, this is definitely going to be one of the harder problems we've tackled all year. It's going to be a little extra confusing because we're working in terms of p instead of an actual concrete number. But anyway, for what values of p does that family, 1 over x to the p power, that p should be underneath that fraction sign, for what values of p does it converge, and then for what values of p does it diverge, okay? So when we talk about integrating this rascal, and like I said, we're interested in the region from 1 to infinity, so we're actually kind of going back to yesterday's lesson in terms of an improper integral, a little easier to identify. We're going to rewrite this, first of all, from the integral from 1 to b, defined as the limit as b approaches infinity, okay? And then I'm just going to rewrite the integral as x to the negative p power, okay? My integrating it says that the antiderivative is x to the, we're going to add 1 to that exponent. We're going to divide by the new exponent, okay? And we're going to say the bounds are 1 to b, okay? Not too bad so far. Remember, x is our variable. So it's the limit as b approaches infinity. Okay, b to the negative p plus 1 all over negative p plus 1 minus 1 raised to any power is just 1. So that at least got somewhat nice. Okay, the next trick that I'm going to use, okay, I'm going to factor out my GCF. 1 over negative p plus 1 is my GCF. And basically I'm factoring that out because it's just a constant, and it really does not impact whether we end up converging or diverging in the end. Okay, I'll say that again. A constant, whether you're adding a constant, multiplying by a constant, is never going to affect the final outcome of divergent versus convergent. Okay, because 2 times infinity is still infinity, 2 plus infinity is still infinity, etc., etc. Okay, now my ultimate decision is trying to decide, okay, when will this expression converge or diverge? Okay, so here's where it's going to get a little deep. It all comes down to that exponent. Okay, for instance, if that exponent up there in the red box, if that exponent is negative, think about what would happen. We'd end up rewriting that first term as, 1 over b to some power, okay? And once that b's in the denominator and b's approaching infinity, guess what? We have small over large. That term then approaches 0, and we would say that that improper integral now converges, okay? That's the most important part of today's lesson, basically, and don't be afraid to replay and rewind those last 3 statements I just said. The next option is perhaps, what if that exponent right there happened to be positive? Okay, what if the exponent up there in that orange box happens to be positive? Then what happens is we'd leave the b where he is in the numerator. Okay, then as b approaches infinity, we have large over small, and large over small says that we approach infinity, and therefore that improper integral ends up diverging. Okay, so that's the big basis for what we're going to base this on. Now, okay, let's go back to the first case. What if the exponent was negative, okay, aka less than 0? I'm going to go ahead and I'm going to solve for p. Okay, I'm going to subtract the 1 over, and then I've got to divide by a negative number, so actually that inequality sign flips, and basically we're going to say anytime p is greater than 1, that integral will end up converging. Vice versa. What if the exponent was positive, aka greater than 0? Negative p is greater than negative 1. Divide by a negative, and we say p is less than 1. So anytime p is smaller than 1, we end up with a divergent series, okay? Which I think, now go back to that graph we just made on the last page, okay? Do you remember when we said, 1 over, let's see, we said 1 over radical x is going to diverge, right? Well, guess what? P in that case was equal to 1/2, which does satisfy that statement right there. Okay? By comparison. Do you remember how we said 1 over x squared is going to converge? Okay? In that case, p is equal to 2, and that does satisfy that statement right there again. So those are just 2 particular examples, but basically anytime p is greater than 1, it's going to converge. And we're going to talk more specifically, of course, I hope you're wondering, I hope someone out there listening to me is wondering, what if p is actually equal to 1 itself? And we'll take a look at that case later on in the chapter. Well, hope you had some good luck tonight. We're going to tidy it all up tomorrow, and we'll be done with improper integrals. We'll see you later.